theorem of calculus. Okay. By the way, for your understanding, a lot of times you may also hear people out there refer to that as the FTC, right there, fundamental theorem of calculus, right? And so you will be surprised about how they're calling that out there. But so I believe I also mentioned that in the first day when I introduced this, I referred to this as the fundamental theorem of calculus, but part 2. Did I say that? On the first day when I introduced it, that nice result that, hey, anytime you are doing an integral from a to b on a function, right, and provided that your function is a continuous function over that interval over here. And the way of doing this is simply finding the antiderivative, right? And then substitute that in, find the antiderivative, then evaluating in from a to b, which means really you're going to substitute b into your antiderivative and substitute a into your antiderivative and subtract the two. Okay? But that's very nice result, right? Really consider historically speaking as part 2. Okay? So what came before this theorem over here? It's called part 1. It's also the fundamental theorem of calculus. The idea now is that, see, originally it was a shock that Isaac Newton proved first that we need to, because right now at this point you see really 2 processes, right? 2 steps in one process here. The first step is to get the antiderivative. That's the bigger step. You see what I'm saying now? And then you're going to substitute in the 2 values to find and to calculate. And so part 2 really just guarantees this result. Okay? But then the part 1, historically speaking, it took time to prove that the part 1 right there is how to know, right? How do we know? How to know to get the, how did you know to get the capital F of x? That's the question right there. See what I'm saying now? Because if that part is false, right? If that part fails, there's no way to use this part. See what I'm saying? So that's basically the connection between the fundamental theorem of calculus, part 1 and part 2 right there. So the one we've been using mainly is this part right there. Think about assuming that this was true, right? Assuming that this was true, the first thing to be done is find the antiderivative. Assuming that was true, then we're going to go ahead and find the antiderivative, and do the calculation. Okay? So now we're going to really get into that a little bit. It's really not a proof yet. It's not a proof. If you want to see the proof, you're going to have to see me outside of class for that. So now we're going to look at part 1 over here. But with the little amount of time left, I think I can just beat around the bush a little bit, and then we're going to get into introducing the actual theorem by the next time we meet. But here's the idea. Now I understand that in our mind at this point, we really love using the fundamental theorem of calculus. We just saw it, right? But think about before it was born. Again, if we're rolling back historically to that time point before that theorem was born, then an integral is only a accumulation. You guys agree? An integral is only an accumulation. And so now let me produce something like this. You got a graph, right, of a function that's called some function f, right? And the variable really at this point is not important. You can call it a function f, t, whatever. See what I'm saying? That. But then think about you fix a point. Fix a point. So this point A right here is the point that you fix purposely. You fix that on the variable axis right here, on the horizontal axis. And then aside from that A point, you pick another point. This point you call it x. Okay? So your variable of the function, you can call it t or z or whatever. And then the point here, I call it x. But this point A is a fixed point. But then the point x here, think about it's a movable point. Okay? A movable point. See what I'm doing there? So here's the thing. If I place the x there, right? Because I said it's movable. I fix the A, but I place the x there. Then if I place the x there, then the accumulation is all the way from A, okay, to x like that. Yes, the way we do the accumulation from A to x is this. Integral from A to x, right? Remember, don't think of fundamentals, of calculus or whatever. An integral is just accumulation. So accumulating the function t, f of t, right, from A to x right here. If we can, think about if we're moving the x right here, then this amount of accumulation changes, right? Are you guys understanding what I'm trying to say with that? If you place the x here, then the amount of accumulation reaches some amount, right? And then if you place the x there, it gets more. And then sometimes, even if your function may, at some point, your function may hit below 0 or something like that, and you put your x here, for example, right? Then still, you got some accumulation positive and some accumulation negative. It net out, it keep adding up more. See what I'm saying? No? But the idea here is that you can, for this accumulation, it's not a constant value. It's not a constant value accumulation, but instead it's a changing value. We can call that it's a g. It's a g of x. Are you following me on that? The amount of accumulation is a function g, but it changes value depending on where you put the x, right? You guys agree that? Okay. See, like when you put the x here, the accumulation is only that much. And you move the x further out, right? You get more. Or if you change the x further out, you get more. Or even in that case where your function swings up and down around the x-axis all over, right? If you put the x here, you get this much accumulation. And then you drag the x to here, for example, right? You put your x here, that accumulation go positive, and then to balance out with some negative. See what I mean? But in the end, your overall accumulation amount, right? We call that as a function g, but dependent on the x variable where you put your x. You guys know that idea right there? Okay? And so, in that way, right here, this is what the fundamental theorem of calculus, part 1 is saying. Okay, so, let f be a continuous. So, I'm purposely letting go of the variables. Naming of the variable does not matter. Let f be a continuous function on some interval. Okay, B. Define. Okay, we want to define this definite interval as some function g of x. So once we have that definition, it holds that. Here's the important result. Taking the derivative of this function g, okay, it equals to the derivative, but that function g comes out easily as just x. It was a shocking result that was found, and I'm going to get some more explanation into that. Keep in mind the picture that I already had over here. Okay. The function g, think of the function g as an area accumulation. So we define g as an area. The g of x here depending on x, right? It's accumulated area. It's accumulated function. But then, shockingly, Isaac Newton proved that taking the derivative of the accumulating function will make it equal to that function f right here. And that's the idea. I mean, that's just stating out the theorem right there, right? But then the formal proof is really nice. I mean, normally in these days we don't have time to cover that in class, so if you want to see the proof, how he proved that, then we'll then see sometime after the class. A little bit. Last time, it's okay. Okay. The idea now is that mainly, so we briefly looking back at from last time, what we did was, so the function g here is some function that's defined as accumulated area, right? And so I gave that the illustration that you got a curve, right? And we fix the point A with here, but the point x right here is we're going to be moving it. And that's why as we're changing the x to either closer or further away from that fixed A right here, then the accumulation that's happening from A to x right here, yes, it's a function, right? It's a function that depends on where we place x. And so it was proven. That's why now the main part of the theorem here says it holds true, right? It holds that the derivative of g turns out to be shockingly that function f. Okay. And so this was a theorem in a way how you see that it's the theorem that really unlocks the key that anytime you're taking anytime you're taking a definite interval accumulations, the action here is you're taking the reverse of a derivative. Okay. And so with just this result right here, we are able to do a few theoretical kinds of problems here. Okay? And so for this, a few examples I'm about to come up, you guys need to think a little bit more abstract, okay, in terms of the kind of problem here. So let's call it example 1. Let's just find the derivative for function g of x, right? If how about function g here is defined as accumulating integral from a value 0 to x, and comes to our function, let's say cosine of t. Okay. Go ahead, spend some time writing it down here. Now, the idea I want you guys to make to avoid this common mistake when I introduce this elsewhere, very commonly, because it's the way it is. It's easier to learn the second part of the fundamental theorem of calculus. So it's so easy that my students fall into this misunderstanding right here that they're gonna first calculate g of x by doing get the antiderivative of that. See what I mean? They do the minus sine of t function, right? Which is very proper, okay? And then we evaluate from 0 to x. Okay, that's what they think about doing it. According to what you guys have learned, similar to what you guys learned, and then substitute that in and get sine minus sine of x, and then subtract the negative sine of 0. See what I mean? Okay, and then that means you come out with a final function here being because sine of 0 is the end of 0 anyway, right? And so you come up with a function here being a minus sine of x, and so you call that your g right here. See what I'm saying? It sounds like a working plan, right? Seems like a working plan. And then it comes to and so that's why it's leading to the g prime right here being taking the derivative. Now, once you know your g, right? That's, like I said, that's the plan of a lot of my students at other places mistakenly fall into that path here. And then they go into like a cosine of x. See what I'm saying now? So as far as getting the answer, yes, that is correct. But the point now is that you are already violating the history. See what I'm saying now? This result was not born before this. Okay? Got the idea right there? That's why doing it this way, you are cheating around in the time history, that the historical time that this result was not born. You didn't even know to evaluate, right? And how do you know this will go into the antiderivative? You have the idea of that right there? Okay? And so for that reason, yes, all you have to do is, according to the fundamental theorem of calculus, part 1, we learn all you see is that with this, in the way how we define this function g as an accumulation function, right? A function that happens by taking accumulation. And so, yes, FTC part 1, right? Implies that g prime has to equal, now see, the cosine of instead of t as now it goes at. It takes just one line, but simply it's just because we have that fundamental theorem of calculus part 1 that allows us. Okay. So we recognize g of x here as the accumulation function. So this is the statement that we use the fundamental theorem of calculus part 1. And by the way, I believe I mentioned that the FTC stands for fundamental theorem of calculus, right? From some of the earlier times we did together. And so the example I brought here seems like that seems like a little bit beating around the bush here, but you guys will understand a little better in the next problem of the same kind of example over here. Okay. So here's the next one. That's going to make it fascinating right here. And that really breaks away your habit of using the evaluation, like the f of b minus f of a over here. What if your function g as accumulation function is defined as a point from, and really the low point here, I can really pick pick any value, like I say a 2 to x here, okay? And your function here, let's say it's a sine of t squared. Sine of t squared again. Go ahead and spend some time writing it down. Okay? Okay, ready? See? So this is clearly making it, or this problem is making it so clear that if you were thinking about finding the antiderivative and substituting it, go ahead. What is the antiderivative for this function?
I'm going to go on a whim here and say sine equals x minus 2 squared. I don't think it's correct.
I mean, I'm asking you guys to think about. I mean, if you're thinking about getting the antiderivative for sine of t squared here, okay? What's the antiderivative for that? Now we use that symbol for antiderivative. Right? What's the antiderivative for that? Okay, we all now live in the world of technology. If you guys bring your mobile device or whatever, right? Hop onto Google, ask Mr. Google. What does he say about antiderivative?
It's no elementary antiderivative is a DNA. There's no way this is true. This is a DNA.
Yeah.
Okay, it's a DNA.
Yeah, so some guys say DNEs, right? Keep searching. You see?
I mean, it's not
the
saying...
point is, Google doesn't know everything, right?
Yes. I mean, it's not saying that we can't solve this problem.
Yeah, I'm not saying we can't solve the problem. As a matter of fact, there is an antiderivative, but it has to take you guys a much more advanced math level to get there. It's not common to the point that it saves you with Google. See what I'm saying? Google only knows the common stuff, but when it comes to the advanced stuff, it's still within the inner circles of the people who are doing math seriously. That's all it is. Okay? And that's the point. We don't know the antiderivative. That's why that path that they would, hey, get the antiderivative and subtract. I mean, substituting the upper bound and substituting the lower bound is going to be hopeless. So that route is clearly out. See what I'm saying? But then, thankfully, the idea now is that all we do is we realize that this g of x is the accumulation function happening from a fixed point, right? Accumulating from a fixed point to a variable value here on that function, whatever that function is. And so, by that way, what I see now is the fundamental theorem of calculus, part 1, right? The FTC part 1 is now simply implies. This is indicating us implies, right? Implies that the derivative of that accumulation guaranteed by the fundamental theorem of calculus should say sine of x squared. Really? That. I mean, whatever the antiderivative will be, right? I mean, if we like I said it before, if we really spend time looking for that antiderivative, it's good luck with that, right? But now we can find the derivative for that easily, for that accumulating function so easily, and that's simply just sine of x squared. That's the whole point. Okay? That's what this fundamental theorem of calculus proves for us. That's what it is. Just think about it, just a few years from now, when you guys take this idea seriously, a few years from now, if any one of you happen to become a stats teacher, and you're on the need of writing a program to calculate like a probability inside a bell curve, thing like that, this kind of understanding will come in. Okay. But anyway, so now example 1 is simple. It's pretty straightforward. Example 2 is going to be similar, but I purposely put that into a new class of problems here. We're still going to find g of x. Now, so this is the part where we're going to need to extend the fundamental theorem of calculus, part 1 here. So I'm going to just call that one problem. How about g of x is defined by accumulation that goes from, okay, I'll fix a point, like say 1, right? And then I'll go to x cubed plus 2x. Okay? And then our function here is e to the t dt. So, what makes this problem unlike those problems we've done in example 2, I mean in example 1 earlier, is that earlier, and this is what comes out directly from the fundamental theorem of calculus, we only learned how to define g as a function that runs from a fixed variable, I mean a fixed value, to one single expression x, right? And of a function f of t dt. But the situation now is slightly different. The function g is still an accumulation, but think about on the graph right here. Okay, you got the function f somewhere, okay, A is a fixed value. But then we don't just simply choose an x. See what I'm saying? But you choose a well, you got an x, but in the end, it's not really x. You're gonna have to substitute x into some kind of function h of x first. See what I'm saying? And your h of x here become a value somewhere h of x, so that you're accumulating from a to h of x, not just simply from a to x. But it's still changing depending on x, right? Depending on x, your h of x is different. Your expression in terms of x will get different. And then your function in terms of x, as it gets different right here, it will give accumulation, right? Being different. So I shouldn't even put the x on the axis here. How about the line here is the value for h of x, actually. See what I mean? And x is some kind of a parameter, right? Depending on the parameter x right there, our h value gets different. And then as the h value gets different, then yes, it can be here, or it can be there, or it can be here. See what I mean? And then in that way, that's how it's done right there. And so, something similar to the fundamental theorem of calculus, part 1 can be used here. At least when it says when we're asking for g prime of x, right? In the way how we've been doing fundamental theorem of calculus, part 1 so far, it seems like we just simply take that main core function right here, right? And substitute, replace the variable here with that expression. You guys agree? Right? So e to the x cubed plus 2x. Are we good with that? But then wait a minute, at this time something didn't go right, because now when we take the derivative, think about this. If the final function is some e to the x cubed plus 2x, right? Think about what happened if we take the derivative here. It's going to have to be what? E to the x cubed plus 2x. But we have to multiply according to the chain rule that you guys learned from calculus 1, right? And so we need to multiply with the 3x squared plus 2 being the derivative of the inside of your function. See what I'm saying? Huh? And so in that way right here, as a matter of fact, for this particular example, we need to multiply with the derivative of that substituted expression like that. So it becomes a 3 and multiplied with 3x squared plus 2. And that is going to be our final answer. So in that way, after this example, we draw a little experience. We're going to come back to the other board and we're going to extend that theorem to them. Sort of like an extension. I may want to spend some time extension to the fundamental theorem of calculus. Modify the word. It's awkward. G of x we define, but this time it's defined by some fixed point to some function h of x. See it there? Okay. Then if g is being defined as accumulation function, happening that way of defining this, and taking the derivative of g, right? We're gonna get, yes, it's f of h of x. See that idea again? Okay. But then see, chain rule says it's not when we have anytime we have a function of another function, a composite function like that, right? Then taking the derivative at the derivative level, it's gonna be what? We have to multiply with the derivative of the inside one. Look at that. That's what we know. Okay. So we come to that extension of the fundamental theorem of calculus, part 1 right there, based on this example 2. And so now, after you've seen all of that idea right there, what about when we're in a situation like this? And this time we're going to apply our understanding. Example 3. Let me look for a good one for my example. Bang. Right. The worst news is here. X cubed, actually x squared. The x, sine cube of g of x is defined by that accumulation. So in the end, you can see that x squared, right? And then e to the x right here being the upper bound. This is upper, and this is lower. See what I'm saying there? And so, the number one property that we've learned, because the fundamental theorem of calculus so far always proves that accumulation that happens from the low end being a one, basically one end being the fixed points, right? And then the other end right here is being the variable points. There's a fixed end and there's a variable end here, right? And so that's why, and that's how the fundamental theorem of calculus part one. But here in this case, the situation goes put you guys in a situation where the function can go, and technically, if that's the case, why do we fix one end, right? Technically, the idea now is that we can just let both ends move, and we still going to have accumulation between them. See what I'm saying? No? So think about that situation. The problem like this: whatever the sine of q of t is, it's this curve right here, right? The sine q of t. But the point now is that the low end is a variable end. And then the upper end here is also a variable end. So depending on where the x variable is, right, if the x parameter is, it may make these two comes closer or comes further away. And then we're still going to have accumulation between them, going from that low to the high. That's the idea. Okay, sounds good. And so in that way, and now at this point, like I said, good luck with finding the, I mean, for this one here, Google can still give you some answer, and then somewhere at the middle of the quarter, we will learn some technique to find antiderivative of a high power of a sine function or a cosine function. We will learn that, because that technique is, in these days, elementary enough, and we can learn. But as far as our learning up to this point, we haven't learned that yet, right? So think about getting an antiderivative for this. It's not the route right there. We have to give it out. And so the plan now is that think about as these 2 points or as these two ends here are variable, there's got to be a fixed point between them. There will always be a fixed point somewhere between them. Pick a fixed point between them. You know what I'm saying, no? Okay. And so, x squared going like that, right? And then e to the x going like this, but eventually wins over x squared. See what I mean? Drawing off scale, but e to the x rises a lot faster than that, so will always stays above the x squared function. E to the x right at 0 always stays up there, right? And the x squared stays down here. And like I said, I'm off scale, but the e to the x goes like that, and the x squared goes like this. So there's always a value between them. See what I'm saying now? There's a value between them. And so, and the point now is that at any instant, when we pick a fixed point right here, the fixed point is just playing a dummy role, but we actually need it there. Right? So now, once I pointed out that idea right there, so this is how we're working it out. Let A, right, be a fixed value, right? X squared and e to the x. And in that case, the integral, this accumulation function becomes like this. G of x can be, now, if you guys remember one thing from what we've learned, it's going to be from x squared, the low, to a. We've broken up that integral because I drew that picture earlier, right? Think about x squared is the low at any instant, and e squared, I mean e to the x is the high, so we got an interval, right? And a is somewhere inside between. And so the accumulation has to be, I think it must be legal to break it up into two separate accumulations, right? One accumulation goes from x squared to a right here on that function sine q of t. You guys see what I mean? And then we're going to accumulate that with the other function going from a to e to the x. Okay? Sine cubed t. That's how we're handling it. So in that way, right here, the right-hand side one here is quite simple at this point. But the left-hand, the first one here on the first term here, the variable, the varying side is on the low, right, and the fixed one is on the high. So we got to fix for that. We got a way to cure the situation right here. Right? And I'm saying to cure a situation means that there's a way to tweak around with that. So that first term, I can run that as minus. You see that there minus, but we go a to x squared. Now we fix the situation like that, and then it's a sine cube of t. And then the other one here goes from a to dx. Okay, sine cube of t. See what I mean? Okay, so these are now, think of these as two separate accumulation functions, and your overall g, right, is a combination of these two terms together. See what I mean? Okay. So now we're ready for getting g prime. So at this point, getting g prime of x, right? So the first guy over here, don't forget there's that minus sign, but at least aside from that negative sign, things get led back into the usual thing that we're comfortable with, right? And so now that minus sign, we got minus, right? And then what do we have here? Sine cubed of x squared. Are we good with that then? And then multiply with 2x. Sound good? Okay. And then we're adding. And now the other one here, we got sine cubed, right, of dx. See that now? And then we multiply with according to that extension of the fundamental theorem of calculus, we have dx. The chain rule kicking in right there. So that's how we have our final answer. And then you can decide to rewrite this in a way that you got that subtract the other one, right? But that's completely at your choice at this point. Okay? That's how we're doing this kind of problem. Handles the fundamental theorem of calculus part 1 with them. The historical version that supposedly came out before you guys could do the evaluation. So as a matter of fact, yes, in these days there are quite a few textbooks called the part 2 of the fundamental theorem of calculus. They call it the evaluation theorem. It allows you to evaluate integral. But this is the original idea that guarantees that anytime you take a definite integral, you've got to go through the antiderivative step first. That's the idea. And so, I mean, of course, now if you relate that to the part 2 that we have learned, right? If we cheat around a little bit and use the antiderivative, yes, technically it will come out like that, right? And then think about we can find the antiderivative for sine cube, whatever that is, and we take the derivative, so it comes out with these two. See these two exact things substituted in and being differentiated out. That's all it is. All right. So now that should be enough with the theory that we learned about the antiderivative. So at this time right here, what I need you to do, let's call it example 4 here. Okay? The part about the question here, we're gonna worry about answering that later, but I need you guys to first of all write down the instruction of the problem, or the description of the function. Call that example 4, and then if you need, and make a copy of your graph, make a quick sketch of the graph. So if you need the picture zoomed in, I'll just let it zoom in, but why don't you guys go ahead and copy this information down first. Okay. And then I believe this function is not too hard to draw, so you don't have to get exact. It's some wavy shape, it goes a little lower, right? And then it has these, it's intended to be going through these these easy points that, and it got a peak, not exactly at 4, but that's okay. We can easily draw that again, right? So we've got this graph, right? And then the function A, capital A, number 4, function capital A is defined as the accumulation that goes from a constant value to x, right? And we're back to the simpler cases of the fundamental theorem of calculus. So our wavy curve written on the board there is the f of t, whatever function that is. We don't care, right? That's why, if you want to find an antiderivative, good luck with that, because we only have the graph. Okay, that's the idea right there. But now with the fundamental theorem of calculus, we can go a lot more flexible in that.
I can just count.
Okay, I'm doing things carefully.
Just
I'm not
count.
exactly sure what you mean by count, but
Yes.
let's go in. So here's the thing. Now, once we know the function is defined as accumulation function, right? Then here's the thing. Clearly, according to the fundamental theorem of calculus, part 1, then it implies immediately that a prime of x has to be what? You guys know it. A prime of x has to be what? A prime of x has to be f of x, right? But do we know anything about f of x? The graph. The graph is what we know. See that there? So f of x, or f of t is the same way, but f of x is now a prime, right? So, and f of x has this graph here. Sounds good? So now things relate to your count 1 data again. These values, these x-intercepts here are the values where your f of x, right? The derivative of a, right? F being the derivative of a, crosses the x-axis. Or you have a prime equals 0 here, a prime equals 0. You guys see that then? Okay, so from the graph, you can see that. No. And this is just, I'm running down a gradient process right here, but see from the graph, right? From the given graph. And we have a prime of x, right? Which is the same as f of x. Has x-intercept, right? At where x equals what? X equals 1, x equals 3, and x equals 5. 1, 3, and 5. Okay, see what I'm saying now? So that's what we noticed from the graph, right? And now I need to, after noting that down right here, let me tell you, ready this thing I wrote on the board for a little while already. Right, so in that way, that means a prime at 1 equals 0, right? A prime at 3, right, equals 0, and also a prime at 5 equals 0. All agree with that? That's just the same result. So what does that mean, right? That means the function a itself, right, has critical values. See it there? Remember that term? Those the critical values?
Oh,
You guys all got over with calculus 1, right? So critical values are very the common term for us now. So a prime has, a of x, the function a has critical values at x equals 1, 3, and 5. That's the one important thing that we have to get. And so now, how do we go from deciding the critical values to being a maximum or minimum of the function a? Okay. So a prime has this graph, and a prime has a prime crosses the x-axis at these 3 places. 1, 3, x equals 1, x equals 3, and x equals 5, meaning a has critical values, right? X equals 1, x equals 3, and x equals 5. But how do we decide whether x equals 1 gives me a maximum for a or a minimum for a? You guys remember the sign chart? We did back then, but instead of looking at the sign chart, the graph is telling the story already. Right at 1 and at 3 and 5, that's we don't care because they hit 0, right? But in the interval between. See? And we want to only restrict the answers from, restrict our work, right? Anywhere from x, from 0 to 6. See what I mean? So at least from 0 to 6, the portion of the graph that we are seeing here right in front of our eyes here, then we got one interval from 0 to 1, right? And it's positive here, am I correct? A prime is positive here. The graph of A prime is here. A prime is positive, and here A prime is negative. See that there? Right? A prime. So, translating that graph into the table, making it familiar with what we've learned from Calc 1. Then what's my result here? We don't do the testing point, but we do the graph point here. See? But understanding that this table is key. You got 1, 3, and 5. Right? Remember that? Right. So, our A prime is what? A prime is positive here in that area, right, from the graph. And A prime is negative in this interval. You guys follow it? Right. And then A prime is, again, the positive in the next interval from 3 to 5. Right. Sounds good? And we don't need the test point here. We use the graph to decide these. Right. And then from 5 and anywhere that hits 6, again, it's negative here. Sounds good? So now it's so clear. So that's the behavior, the sign behavior of A prime. So we don't even have to see the graph for A, but we know that A of x has to have what? See, it's decreasing. Whoops, I'm lying already. It's increasing with that. It's positive, right? And decreasing. Now what do you say about that point? It has to be a local maximum here, right? And then what do you say about this interval? The function A has to be increasing and again decreasing, right? So we got max here, maximum here, right? And a local minimum here. See what I'm saying? No? That's how it happens. Okay. So after that decision, then we're going to say, we have, see the question was asking at what x values, right? At what x values does A of x have a local maximum? Right? So local maximum is the only guy here, right? So you're going to just answer x equals 3 for that, right? So A of x has a local. Oh, it's asking the maximum. Sorry, my mind's reading backwards here. Has a local maximum x. So these are actually the 2 points, right? 2 critical values giving us local maximum. So x equals 1 and x equals 3. And when you enter that into later on, if you have a problem similar to this, and it's already have the x equals right there, so all you do is just make a list, and the order doesn't matter. You can just put in like 1, 3 right here. You see what I mean? Okay. That 1, 3 or 1, 5. Right. It should be 1, 5. Okay. I had a typo again. This is how we write it. Okay. A of x has a local minimum. X equals 3. Okay. Track it all down. All right. That's how we're utilizing the fundamental theorem calculus part 1 to answer different various things. So like I shared with you guys a couple times before, but the exact same material right here, the business major people also learn that too, and the life science people also learn that too, like the people who are about to go into health science, they don't have to go into this in-depth stuff. Okay, this information here is intended for people who are eventually at the furthest. They can go into math major with this background, okay, or in some other ends, physicists or engineering. They got to learn that and know these like deep end of the material. Okay, so it just each career the path has its own desire for this material. So teaching a class like this for the business major, I never have to teach into this in-depth side of that. Right? They never have to learn about the fundamental theorem calculus part 1 of that. Actually, there was a time colleges taught them, but they felt it was such a very challenging time, a difficult time for the students to learn, because their applications really don't need them to know that much. Okay, and it's not practical, so they took it out of the learning the curriculum. Okay. Any other questions for me on this stuff?